In this video, we're going to be working some more eigenvalue, eigenvector problems, and I think today we're more focused on the eigenspaces, the algebraic and geometric multiplicities, stuff like that. All right, so first, we're going to start with the eigenvalues and their algebraic multiplicities. So that means I need to find the characteristic polynomial. So I'm going to take this matrix, subtract lambda down the main diagonal. And we take the determinant of that. So that's going to be 5 minus lambda. I'm going to definitely use the first row of this matrix for my cofactor expansion. 5 minus lambda minus times the determinant of that, plus minus 0 of some other determinant, plus 0 of a third determinant. We're going to ignore the zeros. And then what I'm left with, okay, is I block off this row and that column, or that column and that row when I've got the 5 minus lambda. And I'm going to say, okay, 3 minus lambda, 4 minus lambda. Minus 6. And then I'm going to have, all right, so that'll be a 5 minus lambda still. And, with any luck, this thing will be factorable. Otherwise, you're down to trying to factor a third degree, and that's in general kind of a hard problem. Okay, if I do negative lambda times negative lambda, that's lambda squared. Negative 4 lambda minus 3 more lambdas is negative 7 lambdas. And then plus 12 minus 6 is going to be plus 6. Oh, yeah, that is going to work. Okay, so that I can keep factoring 5 minus lambda, lambda minus 6, and lambda plus 1. Okay, now if the determinant of the matrix minus lambda times the identity is equal to 0, then lambda is an eigenvalue. So that means my eigenvalues are lambda equals 5, lambda equals 6, and lambda equals negative 1. Okay, and all three of these have algebraic multiplicity equal to 1 because these factors are appearing once in the factored form of the polynomial. Okay. The next one is going to be told a known eigenvalue. It's known that lambda equals 9. That doesn't seem right. All right, that will work much better now. It is known that lambda is 10 is an eigenvalue of this matrix. Okay, and write a basis for E10, the eigenspace corresponding to lambda equals 10. Okay, so my first order of business is to look at the matrix minus 10 times the identity. If I look at, if I call this matrix A, I need to give it a name. All right, so if I take A minus 10 times the identity matrix, and I would say, all right, so 11 minus 10 is 1, 1, 1, 1. 2, 12 minus 10 is 2, and then 2 more 2's. 0, 0, 0, 0, and then 0, 0, 0, 0. Okay, if I go and row reduce this, I'm just going to get that first row, right? Because I'd subtract 2 of those away. I've already got these all 0 rows. So I'd say the reduced row echelon form of A minus 10i is, I've got the 1's, and then all the rest zeros. And, the null space of A minus 10i, that's E10. That's the eigenspace corresponding to lambda equals 10. So I'm going to be interested in, kind of mentally thinking about the homogeneous system, setting this equal to 0, 0, 0, 0. And that would be telling me that x1 plus x2 plus x3 and x4 added together to equal 0. And that's all it's telling me. So I'm going to solve for x1, and that's going to be negative x2 minus x3 minus x4. And that means that x2, x3, and x4 are free variables and able to be whatever they want to be. Okay. Now, if we're writing a basis for the eigenspace, then I would, I'm just going to write out all the steps since I'm here doing these problems right now. I'm going to say x1 was equal to negative x2 minus x3 minus x4. x2, x's 2, 3, and 4 are free variables, and so I could factor out the x2. The x3 and the x4 and write it as a combination. So x3 times negative 1, 0, 1, 0, and then x4 times, let's see, negative 1, 0, 0, 1. Right, and that means that these three vectors here will be a basis because these are independent, and they are a spanning set. Any vector, any of these eigenvectors x can be written as a linear combination of these three vectors right here. So I'm going to say the basis for the eigenspace corresponding to lambda equals 10 is going to have negative 1, 1, 0, 0, negative 1, 0, 1, 0, and negative 1, 0, 0, 1. In the next part of this question, they asked, what is the geometric multiplicity of lambda equals 10? Give a reason for your answer. Okay, well, the geometric multiplicity is the dimension of the eigenspace. The dimension is the number of basis vectors. Okay, so that means it's dimension 3. Let's say B. I was trying to say dimension of the eigenspace corresponding to lambda equals 10 is 3. Yeah, so maybe something like that. And that would be a good reason for my answer. The next one says, all right, it is known that lambda equals 3 and lambda equals 5 are eigenvalues of this here matrix. The dimension of one of the associated eigenspaces is 1. Write a basis for that eigenspace. Okay. Well, I think I'm just going to start with lambda equals 3 and hope for the best. Okay, with lambda equals 3, if I called this matrix maybe B minus 3I is equal to 6, 4, 0, negative 6, negative 4, 0, that's the same row, and then 6, 4, 0. Okay. And then, let me think. Well, we'd really just be looking for, like a null vector for B minus 3I. That would be a, I think. Oh, no, this one's going to have, this is going to have dimension 2. Because there's two different ways you could get a 0 column. That would be by taking, maybe like 4 of the first column and negative 6 of the second column. That would work, or some sort of similar proportion. Or you could just take none of the first and none of the second and any number of the third. So that one has dimension 2. I would say, maybe I would just point out that rank of B minus 3I is equal to 1, because there's only one, unique row in here. That means that the nullity of B minus 3I, which is going to be the geometric multiplicity, or the dimension of the associated eigenspace, that's going to be 3 minus 1, which is 2. Okay, so that one's out. It's got to be lambda equals 5. It's got dimension 1, and then we're going to write a basis for that. All right. So with lambda equals 5, B minus 5I is going to be equal to 4, 4, 0, negative 6, negative 6, 0, and let's see, 6, 4, negative 2. That's interesting, but I can see that dependence relationship here. Those first two rows are identical. So I'm going to need to kind of like start row reducing here. I know I'm going to have, I need 2 steps. Okay, that negative 6, 0 is going to become a row of all zeros at the bottom. But I think I'm going to promote this one and look at, okay, I might need to subtract 6 of row 1 away from row 2. 4 minus 6. Oh, okay, so I've got more steps. It has 10 more row reduction than I expected. I'm going to change those to 1 and 1, and then if I subtract, I'll have 1, 0, negative 1, and then 0, 1, 1. Okay, this is a good one for us to practice writing the basis for. We're thinking about null vectors here, so we're mentally setting this equal to 0. And so that's telling me, all right, x1 minus x3 equals 0, and x2 plus x3 needs to equal 0. So I'm going to solve for my variables. X1 is going to equal x3, x2 is going to equal the negative of x3, and that must mean that x3 is the free variable. Okay, that's dimension 1 because there's one free variable there. And then I'm going to say the basis for the eigenspace corresponding to lambda equals 5, that's going to be just 1, negative 1, 1. All right. And all right, number 4, it is known that lambda equals 2 is an eigenvalue of this, it's quite a matrix. Got symmetry to it. What's the geometric multiplicity? All right, so what we're going to need to do is basically just check the nullity of this matrix, which I might call M or something. I want to find the nullity of M minus 2I. Okay, because that's the geometric multiplicity is the dimension of the eigenspace. The eigenspace is the null space of M minus 2I. So that's why we're looking for the nullity. All right. Let's see. I'm subtracting 2 down the main diagonal. Okay, that's where I'm going to get all negative 1s in the whole matrix. All right, so negative 1, negative 1, negative 1, 4 times. Okay, I would have been wiser to just say, oh, wait, I know what the reduced row echelon form is going to be. It's just going to be that one row that I've got. And so RREF of M minus 2I. And maybe you can just see that this has rank 1 and you're good from there. I'm kind of realizing I wasn't actually looking for a basis or anything, but I'm this far in, so I'm going to write the reduced row echelon form of M minus 2I. And I can see, okay, there's one pivot, the rank's going to be 1. You can say, oh, there's only one row in there, one unique row in there. So I'm going to say rank M minus 2I is equal to 1. That gives me the nullity of M minus 2I equals 4 minus 1, which is 3. And then I have that's the geometric multiplicity, is the nullity of M minus 2I. Okay, so good there. Moving on, we got one more problem. This problem set. Oh, this is a little different. This is one that didn't put it on there because I put it on a quiz or anything. I thought it was good algebra. So if x is an eigenvector of a, and you don't know a, corresponding to lambda equals 2, I think I'm going to start off with that. I know that means that ax equals 2x. That's going to be for sure. So ax equals 2x. Okay. And then y is an eigenvector of a corresponding to lambda equals 1/3. I haven't really looked too much at situations where the eigenvalues themselves are not integers, but that definitely happens, especially with real matrices, industry and stuff. So I'm going to say, all right, if y is an eigenvector of a, then ay is going to be equal to lambda y for that value of lambda, so 1/3 of y. Okay. And I'm going to probably need to use these two facts when I'm interested in the value of a to the 5z. Okay, now I tried to make it pretty obvious what was going on here, that z was equal to x plus y. Now, what we could do is you could make this problem a lot more robust by figuring out what linear combination of x and y gives z. I wanted it to be obvious the first time I showed you a problem like this. So I'm going to say, all right, z equals x plus y. All right. So I'm going to start small. Az equals a times x plus y. But matrix multiplication does distribute. So I'm going to say that's equal to ax plus ay. But I could probably just do the same thing with a to the 5 times z. I'm going to say, all right, a to the 5 z's is equal to a to the 5 times x plus y. Okay, I'm going to distribute. Okay. And I mean, I don't know if we've thought a whole lot about the repeated multiplication on an eigenvector, but it's just going to repeatedly scale it. So if, and maybe I'll come back and justify that here in a second. But a to the 5th x is going to be 2 to the 5th x. So 32x plus a to the 5 y is going to be 1/3 to the 5th times y. So wait, 3 to the 4 is 81, meaning 3 to the 5 is going to be 243. Okay. And that means I can actually do this. 32x is going to be 32, 0, 32, and 1/243y is going to be 3/243. That's going to be the 1/81. So I'm going to just, maybe I'll just actually show you the addition. Okay, and then that's how what's going to give me my result, which is a to the 5th z. I don't know if that's still visible to you, barely. All right, so a to the 5th z is going to equal 32, 1/81, and 32. Okay, even though we don't know the value out of the matrix A. Okay, now the other thing I was going to show you was this whole thing about like if A's basically repeated multiplication on an eigenvector. So I'm just going to do ax equals 2x. Just think about that. All right, ax equals 2x. Okay, well, a squared x is a multiplied by ax. I'm just like really kind of belaboring the point here, but that's ax is going to be 2x. And so that's a times 2x. And okay, we can associate with constant multiplication, saying that's 2 times ax, and that's 2 times 2x, which is going to be 4x. Okay, so it's that repeated multiplication on an eigenvector works the way you would expect with, like that repeated factor of the eigenvalue. All right, that's number 5. That's the whole problem set, so that's going to be all for this video. Thanks for watching.